Hi, my name's Julia. I used to work in Rosetta mission as a planner, giving science support for operations. So that's why I'm more familiar with the cometary calculations and the language that we use in cometary science that in meteors. But I thought it was a nice idea to bring to you like a summary of all what things that we have learned from the dust particles in Churyumov-Gerasimenko, and then after to try to make a comparison with the meteor sizes and what I found in the bibliography of meteors. So basically, first of all, my apologies for the delay, and I just wanna get into not much details about what is and how all the mission is about, and but specifically how I get the information and what are the constraints and the bias in the data, which are a lot of them. So probably most of you are familiar with the Rosetta mission and the different instruments, but if not, there were a couple of in situ measurements instruments that they just collect dust particles, and they were able to extract the different information from them. There were other instruments that we used for taking images of the field of view, same way that you do in your house. And with this, we are able to calculate the trajectories and estimate more or less the mass of the particles. And and there are other instruments that they were not directly related with the dust particle science, and we didn't use them for this. So after several years of calculating and analyzing all the data that Rosetta mission got, we have like a big model of how the dust particles behave in the near surrounders of Churyumov-Gerasimenko. So at first, one thing that was very surprising is that around 95% of the dust particles that are ejected from the comet are in certain moment redeposited into the surface of the comet. So you could see here in the table a little of the summary that when there is an intense activity in one of the hemisphere, in the southern hemisphere, lots of jets and lot of particles are ejected, but in certain moment they are redeposited because the velocities and the trajectories are not open and the particles are not ejected into the coma. And then after it's we have been seeing through some visual images of the surface that all these movements in the northern hemisphere is changing and is having some activity along the time. So the process is much more violent than we thought at the beginning, and this has to be to take into account. I'm not gonna go deeper into this, but this is a small summary about the values of the distances and the dust activity that we have found with different papers. What is important to understand is, apart from these images, that for me is the most important one because it's really clear how the dust particles are evolving from one side into another, is that the basic model of the structure of the comet made in layers is still valid, but it's much more difficult to understand when you have the depletion of and the sublimation of some of the material, and then after a redeposition, when you have a mix of different type of particles and boulders inside the surface of the comet. So once the particle has been ejected, we could estimate more or less what will be the forces, as you see here, the solar radiation, thermal reflection, but you know more than me about it. And finally, to take into account in this analysis, the different types of particles that you see here, mostly divided into porous, with different size, and a fluffy particle, right? That the behavior is going to be different in terms of measurements, mostly in the in situ measurements, and that will generate some bias in the data when trying to calculate the diameters. And the other big bias that we have is reflected in the table and in the graph. Is the same data. Is that not all the instruments of Rosetta are having measurements in all the sides spectrum. So that means that in certain moment we will have some bias in the number of particles, not because they were not particles in, for instance, centimeter sizes. It's because there is a gap in the measurements. And of course, not all the instruments were on during all the mission. We weren't pointing all the time into the same direction. So there are always bias over bias. But compiling certain papers and some data sets that they were extracted from different instruments, I was able to do this logarithmic histogram of particles of particle sizes versus the number of particles. And at first it's not very easy to interpret. But one thing that is for me is very shocking, and we are working on trying to extract more data from that, is that large boulders are really difficult to observe when they have been ejected through 67P, which is curious because the big boulders are quite easy to see in images. So maybe there are not that many big boulders. When I say about big boulders is over 1 meter diameter, than we might expect, or maybe it's because we don't have enough data and we were unlucky in terms of when we were observing. One important thing about it is those data sets are not, I just choose the data sets that were not really close by the surface of the comet, because otherwise those particles were going to be redeposited in certain moment. So the only particles I'm interested on for comparison with meteors are the ones that are really far away from the surface, that they are not going to have to fall down again. So that's the reason why the data sets are not that huge. And the red one is one big boulder that we discovered like a couple of years ago that we call him Churyumov, and is the only one that we were able to determine the trajectories being ejected out of the comet, and it was around 4 meter diameter. So well, in a not logarithmic scale, you could see better the profile of the sizes. And trying to make like a Gaussian about the data, I try to be very aware about the bias of the data and the information. And I still have to work a little bit on that part, because I'm not completely sure if the values are completely correct, because I have to reduce some of the data for having the information, and I want to extrapolate into meteors. But what is interesting is something that Jan Santal made some years ago, that is the power index of the size distribution, depending of is this pre-perihelion and post-perihelion, which is an important information as well. I forgot to say that in the previous graph, I used a variety of data sets from different moments, but all of them are inside the 2014 by the end of the year, and end of 2015, which is the moment that we were going into the perihelion of the mission. Of course, there are more. Sorry, I think I'm late, right? Okay, good. This study at first is not gonna enter in any other thing that they weren't sizes, but it's true that you have to take into account what is the velocities and what is the escape velocity of the particles, and I just took it more or less the ideas from Moreno, the paper. And of course, now that we have more or less the overview of the size distributions that I took in the data from Rosetta, how do you compare with the meteors? Of course, the first approximation is just using the Jupiter family meteor showers, not other ones, because in composition and probably in size distribution, they should be more similar to these meteor showers, right? And what I didn't consider at first, because I was I was hoping that maybe you could help me with that, because you are more experienced than me. It's all the bias that you observed in the meteoroid's size distribution when you evaluate the meteor streams. So I ran a little bit out of time, because I'm doing all this in my free time, but I was able to extrapolate some data from Boropika, from 2P, and compare with the data that I show you before, but just in the range that of particles that I found in this paper. And at first, my idea is that the results are fine. I mean, it's not like a big difference, but there are not many conclusions to extract from this table, really, because it's true that it seems to have like a kind of tendency trend similar, but there are many differences, mostly when you evaluate the different orbits, the different shape of the orbit, and how these particles has been moved or transformed because of the different forces of the solar system, right? So as conclusion for my previous analysis, the first thing is we were expecting larger particles in the data sets of Rosetta. That it's fitting more with what I read in the bibliography of the meteor showers, that you find the large chance of particles. The curves from 2P in comparison with 7P, it's under investigation, because there are many different bias in the set of data. And this is mostly because of the instrument constraints from Rosetta, and of course, because of other constraints that I'm not that familiar in the meteor showers. And I didn't take too much number of data from meteors, and that's why I'm showing this, that I would love to improve this study with more and more data, and probably some of you might be interested on helping me with the analysis of the meteor showers and trying to make like a big plot of with all the possible different meteor showers. So my idea in the next weeks might be to add more comet showers from, for instance, 10P, 1P, or 55P information, and I will be super happy for any other collaboration that you would like to have with me. And well, mostly I think it was it. With the nervous of the presentation not being there, I'm not sure about what time is it. So
I think you had quite some time, so I think